Yo! Welcome back to the development diary of Saikyo, the cross-platform language learning app. Last time, we started to code up what we think the UI is going to look like, and I introduced a little bit about the composition. And I mentioned in the very last episode that before we start emitting widgets directly into the UI, we're going to need to do some prep work for the composition itself, because we don't have any of our standard types. Up until now, we've just been using type defs and or order to stick things into our code. But we're going to need to have fixed with integer types because we'll be making a memory arena probably in this episode too. So let's go ahead and let's start with making our fix with integer types. Now, if you're following along in my other series, the Umi compiler project, then you've probably seen this trick before already. But if you haven't seen that yet, then please check it out. It's pretty cool. But the trick that I'm going to show you now is the exact same that I did there. So how do we do it? Well, first, how does the compiler do it? How does the compiler know how big an int is, how big a long is, and things like this? Well, the compiler can cheat. And I guess it's not cheating. The compiler knows because it's the compiler which is taking the text of the source code and turning it into executable machine code. And as a part of that, naturally, it needs to know how big the integral types are. Otherwise, it's not able to properly transform the code into things that will fit in registers, do register management, things like this. So the compiler knows already. It's just hard-coded into the compiler. Sometimes there are things like built-in int8s. As you can see, there was a very slight syntax highlighting there. Naturally, that varies between compilers. So we can't take advantage of that. But what we can do is that we can test for the size of various sized types, and we can set our own type defs accordingly. And the way that we can test for the types is not going to be through the preprocessor, because the preprocessor has no knowledge of what an int is. It has no knowledge of what any of these things are unless the compiler has hash defined them. So instead, we're going to have to drop out from the preprocessor, and we're going to have to use the language proper. And the way that we're going to do that is with templates, template metaprogramming, which is, some people love template metaprogramming, some people hate it. I see it as a necessary evil because C++ doesn't have metaprogramming, which is up to the standard of, say, Python, or I guess that's not true. The most recent version of C++ has metaprogramming, but in true C++ fashion, it is absolutely horrendous. Anyway, that's neither here nor there. Let's do it. So the way that we're going to do this template metaprogramming trick is we need to create a conditional if statement. It's going to be an if statement such that we'll pass it this if function thing, a compile time evaluatable question answer, which is represented by this bool. And then depending on the value of the bool, if it's true, then the answer will be this true type, T type. Otherwise, it'll be F, this false type. Now, the trick with template metaprogramming like this is usually you have a default answer to a question. And in our case, we're just going to set the default answer to the question to be F, which is false. And to get to the true side of the question answer, or to provide more specialized answers to whatever that question is, that's where you would use C++'s partial specialization trick. Partial specialization is basically you have a primary template and you can fix one of the template parameters and then you let the other ones vary. And for all of the classes where that fixed parameter is the value that you think it is, then it will select the more specialized template rather than the most generic template. So what that looks like concretely for us is in the events where our struct if template is being evaluated with the value of true and still T and F, that's when we'll set the type to be true. So what this means is that if ever we're evaluating this if struct with false, it will choose this, the primary template. And if we're evaluating it with false, then it will with true, then it will choose this template. And as you can see, when it's true, we choose the true type. When it's false, it chooses the false type. So we get the best of both worlds. And from C++ 11, they also introduced the new using syntax. And you can, I think, unlike a type def, you can also make a template out of that. And people usually do. They'll say type name, if CTF type, like this. And the reason why this is useful is because you see in C++, whenever you have a struct and then you access a member of the struct template, I should say, or a class template, it will expect the thing on the inside to be of a value, like a member variable or a function. But in our case, this type thing is a type def. So you have to put type name before for the compiler to know that you're actually talking about a type. For example, if this was actually a template, then there's also a keyword for template, but we have a type. So this is purely C++ only syntax, and I don't have syntax highlighting right now. Can I? It's very strange. I don't have syntax highlighting, but it's whatever. Probably what's happened is that the Clang, what did you say? Actually, no, that's not true. Probably the reason why this has stopped working is because, no, that's not true. I was thinking, you see, C-Line has two like parsing engines. It has C-Line Classic, C-Line Nova, and C-Line Nova doesn't support AppKit. It doesn't support Objective-C. So I was thinking that maybe this is because we accidentally switched over to C-Line Nova. Let me actually just check that. Because I would like... No, we're not using C-Line Nova. Looks like the Clang parser is just literally dead. One of the many reasons why I'm doing the series is to eventually replace all of these tools, but I guess that's, well, future dream. Anyway, we don't need to care about that right now. The point is that by using this if-t alias, we make it a bit easier to access this if struct thing, but it's completely optional. But from here, we can go ahead and we can start creating the types that we want. So we can say int8. Int8 is the easiest one because char is always going to be 8 bits for modern machines. So that's not very interesting. But for int16, it will be interesting. In 16, we can say now if-t, if the size of a signed short, I guess we'll just say short, is equal to 2 bytes, then we'll make the int16 type be an assigned short. Otherwise, we'll make it a signed int. And the reason why we need to do this is because on some platforms, int is also 16 bits, which I think could be the same size as a short. However, most people would agree that nowadays int is usually 32-bit. But for those 16-bit platforms, we need to check. But I guess where it's a bit more visible to see would be potentially int32. So if the size of an int is 4 bytes, then we'll make our 32-bit fixed-sized type be signed in. Otherwise, we'll make it signed long. And this is, again, for 16-bit platforms. If int would be 16 bits on that platform, then long would be 32 bits. And so this will check for us. And then finally, probably the most contentious is int64. So if the size of a long is equal to 8, then our int64 type will be assigned long. Otherwise, it will be a long. And this actually matters on, say, Windows. On Windows, a long is still 32 bits. The Windows like D word, which is their data word type def thing, is a long, and it's only 32 bits. But on Linux and on macOS, a long will be 8 bytes or 64-bit. So even for modern machines and modern compilers, this type def is actually completely necessary. Although I suppose you could argue that since signed long will always be 64-bit, you could just make this a signed long like we did with signed char and not have this conditional. But just for even demonstration's sake, we're going to keep it like this. All right. So we got our signed types. Let's go ahead and stick in our unsigned types. So you, my friend, are an unsigned char. Let's be real quick with this. Boom. Ah, damn it. Wait. Can I make it so that it will align? Haha. Unsigned. There we go. All right, sweet. And finally, what I like to do is I also like to define the floating types. So a float 32 will be just a regular float, and then a float 64 will be a double. One of these days, I would really like to make float 16 be like a half, but half is still not defined in C and C++. Some compilers, they have like a built-in half type, but I think even you need to hash include another header for that. Apparently OpenCL has it. But I don't want to do that because I don't want to include any headers into saikyo-dev. So for the time being, I suppose we'll just go without that. And technically there is a long double type, but on Intel, that's like 80 bits. You would think it would be 128 bits, but it's not. So for the time being, we'll just stick with 32 and 64-bit. Okay. Now there's usually two other type defs that I like to have around. One of them being size T. And size T is dependent on the size of a pointer. So if the size of a pointer is 4 bytes, which is 32-bit, then we'll make signed T be our unsigned uint32. Otherwise, it'll be uint64. I guess technically this isn't correct. And the reason for that is because just because a pointer size is 4 doesn't mean that when this is false, i.e. not equal to 4, it's equal to 8. Right? It could be equal to 2 on some weird 8-bit platform. So even this would have to have like a few nests of an if T. I guess you could generalize this, maybe. But for the time being, I will make size T just be one of these two. And then one more type that I really wish they would standardize for C and C++ is the signed size type, because it's good for the completeness factor. Now, if I recall correctly, this could break AppKit because AppKit also defines its own types like this. Right. So where is it? It thinks that a uint64t type alias with different types. So it thinks that an unsigned long for AppKit is, the int64 type. AppKit has defined it to be an unsigned long, but we just defined it to be a long. So these are conflicting. And there is actually a way to get around this. I believe if you come up here, yeah. So one thing Apple did really nice is that they put these guards in, so that way you can prevent clashes. So if we define this uint64 type, then we should be able to get around this. So if I just say hash define u, then this should be okay. And look at that, completely fine. Awesome. Okay, cool. So now we have our fixed width integer types, and we also have syntax highlighting back again. So it's a win-win for us. I reckon that deserves a swig of my tea here. All right, so the next thing that we can tackle in this episode And probably the last thing that we'll do is I want to talk about the memory layout for composition. So what I'm thinking for composition is, because we're just going to have a kind of like, one thing that modern UI libraries do is they'll have this, right? Like they'll have something. Actually, why is this still called something? We should call this composition. Right. I think I showed this a little bit before as well, where we're going to have like, order some widget equals da 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 da, and then we'll like further compose like composition. Just grab everything here. Composition, and then maybe we'll create another like nested widget. And like this, the structure of the UI is represented in the code with these nested function calls. And what's cool about having this composition thing be explicit to the user is that every time you do one of these calls, we're literally going to be allocating the memory for the widget as we go down and as we pop back up. So what it will look like is that every widget will literally be in its place at its indentation level. So we can allocate all of the widgets as though they were just in a line, like we can allocate the widgets linearly. So I want to represent that inside of our composition structure here. And the way that we're going to do that is we're going to use a linear allocator. And my general way that I do linear allocators is I'll just make a struct called MemoryArena. And MemoryArena here is not specific to linear allocators. I use one of these arenas for everything. Stack allocators, linear allocators. This might be your first time hearing about allocators, and if it is, don't worry. We're going to see tons more of them as we go forward, but the idea behind an allocator is that you have just a flat array of memory. So for me, I'm going to limit the size of the MemoryArena to 4 gigs. I suppose we can always make a bigger one if we need to. But I have a current and a capacity, and I have my bytes here. So I'm going to stick one of these MemoryArenas inside of composition, and we'll call this widgets. And so like this, once we give memory to the composition, as we go through with compose, we're going to slowly increment this current pointer with the size, by the size of the widget that we are making. So that's pretty cool. Let's give some memory to widgets. Let's do that. So now we actually have to give some initialization code to UI, since now something is not something and it is in fact a thing. And this is still being shown as something, but it should update. I guess C-line is buggy today. Okay, so we're going to pass it one of these composition things. So let's do it. Am I passing a pointer? Yeah. So where should we stick this? I guess we'll stick it right here. So what we'll do is we'll make, maybe we'll call this UI comp. And this will be a composition. And the next thing we need to do is we'll say that the comp widgets current should already be 0, so that's okay. In fact, what I'll do is just copy this. Okay, so current should already be 0, so that's no problem. Now capacity, let's just be generous at the start, and we'll give this thing 8K. Do I have? I don't. Some convenience functions I like to have are functions like this. So we'll make a const expr static order. I think static goes first, actually. Static const expr order kilobytes. So we'll take whatever n is, and then we'll just multiply that by 1024. and I'll return that. And while we're at it, usually if you want kilobytes, you also want to have the other units, wouldn't you? So megabytes is going to be however many kilobytes this is times 1024. So this is going to be now MB. And finally, I will also add gigabytes. And this will be same pattern, just megabytes. So if you want 3 gigabytes, that is not 3 megabytes. That is the wrong thing. This will be n times 1024 megabytes. And this will be n times 1024 kilobytes. And that should be correct now. Oh, wait, hang on. No, this is wrong as well. What am I doing here? No, I think I had it right the other way around. Make that GB as well. Wait, let me think about this for a quick second. So if I pass in 3, that's 3 megabytes times 1024. Yep, that's right. No, I did have it right the first time. Just a brain slip. Sweet. Okay, so if we come back into AppKit, so what will our capacity be for... Oops, I don't want that. I want this. The capacity, will give it 8K to begin with, so that'll just be 8 kilobytes. Now for bytes, where will bytes come from? So this is the interesting question. You might think that we'll just whip out malloc, but do we actually need to do that? There's actually a trick here that you can do to make life a whole lot more interesting when it comes to memory allocation. And I think what I'll do is I will leave that trick for another episode. And for the time being, we will just use malloc. So to get access to malloc, we can either hash include c_lib, but that's kind of blasé. So what I'm going to do is I'm going to do what you should never do is I'm just going to declare malloc myself. You see, whenever you compile C or C++, the C standard library is going to basically always be linked in with your executable. So you can just define the C standard library's function prototypes and be rest assured that it will link automatically for you, which may or may not be a good thing, by the way. We might want to one day remove the C standard library, but that might be impossible for AppKit because AppKit also uses malloc underneath the covers, under the hood. But if we do that, that'll be pretty interesting. So I won't put the trick here for now. Instead, we will simply just malloc. My friend, you are an UN8. We will malloc this capacity. And for good measure, I will assert that you are not null. Because if you are null, there's nothing we can do. Life will be hard. Okay. So there we go. We have memory for the composition. We've made our fixed width types and our fixed width floating types. And we did a little bit of template metaprogramming. So we're in a pretty good position to start writing this compose function and in a pretty good position to start fleshing out the UI code that will form the basis of our apps GUI going forward. So I'm pretty excited. This is going to be very fun, I think. The UI hopefully won't be as heavy and hard to deal with as past experiences with things like Jetpack Compose and Swift UI, UIKit, AppKit, things like this. But that's all the time that we have for today. Thank you so much for watching this development diary of Saikyo, the cross-platform language learning app. Next time, we're going to flesh out more of this UI, and we're going to have I suppose, a talk about making this a little bit more usable. So thank you so much for watching again. If you have any questions or comments, feel free to leave them in the comments comment section, and I'll try and get to them. So have a good day. Take care.